Okay, welcome back. We are finally going to finish our sections on elliptic curves over local fields. And the last piece that remains to study is this quotient, the quotient of E over E naught. Why? Well, remember that, let's just remember what E naught was. So E naught of K was the points of non-singular reduction. Okay. Like that. And remember that E1K was the kernel of reduction. So from E naught down to E and S. Okay. And that all these fit in an exact sequence that goes from E1, which is, by the way, isomorphic to E hat M. That's why we spend so much time looking at formal groups, and E naught K and E and S K 0. So when we have good reduction, so when there is a good news, when there is good reduction, then we have that E1 injects into EK, and this maps down to the reduction, which is an elliptic curve. And we understand everything here. It tells me the structure of EK in terms of the two pieces on both sides of the exact sequence. But when there is bad reduction, we do have this exact sequence, but we still need to understand. So we understand this piece through the formal group. We understand this piece through the fact that we have an isomorphism to over K bar to K star or K plus. So what we need to know is how far is this from the entire group E over K, okay? So we have that this is inside E over K, but for all we know, this quotient or this inclusion might be huge, or the quotient of one by the other might be huge, and then we're really far from understanding EK. So the answer is that no, we are pretty close, and this is a theorem of Kodaira and Neron, which is part of the advanced topics on elliptic curves that one would learn in the second volume, which is if you have an elliptic curve over a local field, then first, let me write this in sort of two cases. If E over K has split multiplicative reduction, then the quotient of E over E naught is just a cyclic group of order. The order is nu of delta. So the valuation of delta, which is minus the valuation of the J invariant. Okay, so it is a finite quotient, and we know exactly the size of that quotient. In all other cases, it turns out that E over E naught, I can't give you such a precise description, but it is a finite group of order at most 4. Okay, so it is just a very small quotient, and therefore, by understanding E naught, we basically understand all of EK. Okay, The key here, so the key and for this result is the existence of what we call a neuron model. Which is not something I'm going to talk about here, but it's a group scheme or a spec of R whose generic fiber is E over K. So, and then you can study the fibers in that group scheme, and that gives you a classification of these quotients of E over E naught, and in it gives this kind of result about the quotient. Okay, this is in the advanced topics. I think there is a very brief summary in the appendix C in the book, the arithmetic of elliptic curves. Okay, so
can I ask a quick question on that?
Yep.
Minor question, but is there like a sort of systematic study of elliptic curves or classification of elliptic curves based on like which of the four non-trivial group structures this affords us? Because if it has at most order 4, then it's either cyclic of order 2, 3, or 4, or it's the Klein 4 group.
So there is such a classification. I don't know that you can see in the screen, but if you go to page 448 in the book, you can see that full classification of, like, I don't know if you can see this picture of the classification of the fibers, and then exactly what happens, what size do you have, and if you have that, what is the classification of the fibers and what it looks like. It's geometrically, it's an awesome picture. It gets pretty complicated, but geometrically you can understand exactly what's happening in the fibers and in this group. Okay, so just read.
Thank you.
Those appendices are great because they're very concise and they give you all the information you need without just sort of like black boxes of very important information. So if you look at that appendix and read it, then you sort of understand what's happening without sort of going into understanding the neuron model, which is something pretty tricky to define. I mean, it's some hardcore algebraic geometry. Okay. So let me just then prove one result about this, which is the following. Knowing that theorem of Kodaira and Neuron, we can prove the following. Suppose you have a finite extension of QP, and then an elliptic curve over K. Then E over K contains a subgroup of finite index isomorphic to R plus. Okay, let me prefer to write it as R over as an additive group. Okay, so this is just saying that E over K is a very large group. So for example, if K is QP, then this is saying that there is a copy of ZP inside the point. So there's an entire ZP copy of points p-adically, so it's large. But it is also a finite index. So you're not too far from being just ZP. The points is ZP and then some finite index extension of ZP. Okay, so let's prove this. So notice that, well, we might have bad reduction, so we have to work with E naught, but E over K over E naught of K is finite. And this is by the Kodaira Neuron theorem. And we also have that E naught over E1K, which is isomorphic to ENS over K. This is finite. right? This is just points over a finite field. Here we are talking, that's why we fixed our local field to be a finite extension of QP, because you can have local fields where the residue field is infinite, and then this wouldn't work. But in here, little k is a finite extension of FP, right? So here, little k is a finite extension of FP. So there's only finitely many points on the reduction curve. Then this implies then that this is finite. So I have a E1k contained in E0k contained in EK, and these are finite index and finite index. Index. So, and then I know that this is isomorphic to E hat. So I just need to know that there is something of finite index inside E hat M that is isomorphic to R plus. Okay, so what we're going to do then, so it suffices to show that R plus is contained in E1k of finite index. But moreover, E1k, which again is isomorphic to E hat, it has a filtration which is I have E hat, and then I have E hat M squared, and I have E hat M cubed, and so on. So this is what I mean by a filtration. And we proved that each consecutive quotient this is just isomorphic. Remember, we proved as groups, it was just isomorphic to Mi over Mi plus 1. This we proved in general for formal groups, which is a finite extension. Okay, so this is a finite group. Again, over the case of local fields, this is a finite extension. So so now I keep going this chain of in the filtration, and I just need to know that one of them contains R plus. But also we proved for large R, or for large enough R, for sufficiently large R, we prove that E hat of M to the R via the formal logarithm, that was isomorphic to M to the R, which is just pi to the R, a uniformizer times R, and as groups, that is R plus as abelian groups. And that is, that's the proof, because what we've done here is find that for some large enough R, and this was, remember, it had to do with the radius of convergence of the exponential map, depending on what your local field is. It has to do with evaluation of P divided by P to the n minus P to the n minus 1, or so, something like that. So, but we've found a copy of R inside one of the copies of the E hat over a large enough power of the maximal ideal, and that is in finite index contained all the way into E hat M, which is E1, which is in E0, which is in EK, and all those containments are finite index containments. So there you go. So you have R plus as a finite index subgroup of EK. Okay, so I think I'm going to stop there. Perhaps I'll just, I think I'll stop here. Next time, finally, we are going to move on, and we're going to talk about elliptic curves over global fields. And we are literally going to start the proof of the Mordell-Weil theorem. So that's going to be exciting. Very good. So I think I'm going to stop here for today, and I will see you on Tuesday.